As we continue to study fluids in motion, one reasonable question to ask is how much fluid passes a certain point in a certain time. The mass of fluid per second that flows through a tube, for example, is called the mass flow rate. The figure shows a small mass of fluid shaded in blue moving along a tube. Upstream at location 2, the tube has a cross-sectional area A2, a density ρ2, and it's moving at a speed v2. Downstream at location 1, the cross-sectional area is a smaller A1, the density is ρ1, and the speed is v1. During a short time interval delta t, the fluid at location 2 moves a distance v2 delta t. The volume of fluid that has flowed past this point is the cross-sectional area times this distance, or A2 v2 delta t. The mass of this fluid element is the product of its density and volume, or delta m2 is equal to ρ2 A2 v2 delta t. Dividing delta m2 by delta t gives the mass flow rate, or mass per second. Likewise, we can calculate the mass flow rate at location 1. Since no fluid can enter or exit the walls of the tube, the mass flow rates past locations 1 and 2 have to be equal. Since these positions are arbitrary, the mass flow rate must have the same value at every location in the tube. This important result is known as the equation of continuity. It is stated as follows. The mass flow rate has the same value at every position along a tube that has a single entry and a single exit point for fluid flow. For two positions along such a tube, ρ1 A1 V1 has to be equal to the product ρ2 A2 V2, where ρ is the fluid density, A is the cross-sectional area, and V is the fluid speed. The SI unit of mass flow rate is kilograms per second. If the fluid is incompressible, as is the case for most liquids, then ρ1 equals ρ2, and the equation of continuity reduces to the following. The product of A times V has units of meters cubed per second, for instance, and represents the volume flow rate Q. The equations above show that when the cross-sectional area of the tube is large, the speed is small, and conversely, when the cross-sectional area of the tube is small, the speed is large. Therefore, the speed of the fluid in the pipe changes as the cross-sectional area changes. You have all probably observed this effect with a water hose, where partially closing the open end of the hose with your thumb reduces the cross-sectional area of the hose and increases the velocity of the fluid.